Okay, chapter 8 in our textbook is all about reaction rates and equilibria. I'll be honest, I don't like the way the book presents this, so I'm going to present it a little bit differently. So let's start out with this really complicated example, right? So let's say I've got a ramp and I put a ball on this ramp. All right, so this is my blue ball on the ramp. Well, what do you think is going to happen over time? Well, most of you will probably infer that this ball is going to roll down the ramp, right? So it's going to go from its original location to a new location further down the ramp, right? There's a few ways we can describe this, right? Number one, we can say that this is less stable, right? It's not happy being up in that higher position. But over here, when it rolls down, it is more stable. All right. And another way of thinking about this, right, is as it rolls down the ramp, it's actually giving up some of its potential energy. So it's giving up energy. This whole process is called a spontaneous process. So let's just write this down. I know it seems pretty simple, but it's going to get a little bit more complicated when we apply this to chemistry. But a spontaneous process is one that takes place naturally without apparent cause or stimulus. Just like the ball rolling down the hill, right? All right, so let's get into the science terms for this, because science actually has terms to consider whether or not a reaction is spontaneous or not. And the term we use for a spontaneous chemical reaction is exergonic. And an exergonic reaction is going to be a chemical process, not always a reaction, I should say, that gives up energy, just like the ball gave up energy. Oops, gives up energy. As it takes place, resulting in more stable products. All right, so it could be a chemical reaction, or it could actually be a phase change, right? So if we undergo a phase change, we might release or absorb some energy. All right, so that's an exergonic reaction. It's the equivalent idea of saying that the process is spontaneous. So oftentimes I remember this by saying that energy is exiting. And so if you remember that X prefix, it's a little easier to remember this. All right, let's do the next one. Okay, endergonic. An endergonic reaction is essentially the opposite. So it is a process that gains or accepts energy, leading to less stable products. And because we're getting less stable products, this is simply referred to as a non-spontaneous reaction. But what I want to do next is define this term energy a bit more, because energy is kind of an abstract concept to think about. And the way that chemists measure this, that they don't really mention in the book, is it is called Gibbs free energy, named after the scientist that really worked with this. But really, it's the measure of available energy that can do work. All right, the book kind of gets wishy-washy with how they define energy, and we'll talk more about that later. There's different types of energy, right? There's heat energy, but then there's potential energy, meaning it's still available energy that could do work, but it's not heat energy, right? So Gibbs free energy is kind of the net sum of all energy, whether it's heat or potential energy, that allows something to do work. So it's a lot more specific. Okay, so let's take a look at some examples. And in these examples, we'll try to make them pretty simple and generic. So let's consider a reaction. And in this reaction, I'm going from A to B. All right. And what we can do as chemists is we can plot this using what are called energy diagrams. So over here, we've got our reaction progress, meaning, all right, we start out as A, and then over time we get to B. And then on our other axis, we've got Gibbs free energy, which I'll call G. All right. And in this example, we'll do something easy. We'll say, all right, originally our starting materials are going to be at a specific energy. So I'll just go ahead and say, all right, A was originally at this energy level. It had this amount of potential energy stored up available to do work. But B has less available energy stored up and available to do work. So if we think about it, right, this must be a spontaneous reaction, kind of like the ball rolling downhill. We're getting to a more stable product. But the cool thing with this is we can actually measure the energy difference. So we can say, well, the energy difference here is just going to be the gap between each of these, right? So if we think about it, the energy of our starting material was a large value versus the energy of our final product, which was a small value. So if we take our final Gibbs free energy and subtract out our larger starting energy, this tells us something important. This tells us that the reaction is spontaneous. So delta G, meaning change in Gibbs free energy, that's final minus initial, is negative. We know that the reaction is spontaneous. And we also know that the products are more stable. They have less potential energy available to do work. All right, so this is a pretty simple example for an exergonic reaction, right? So let's go ahead and include this. So this is an exergonic reaction. Okay, now let's do the opposite one. Let's just say we've got a separate reaction. This one I'm going to call C to D, but this time we're going to flip things around. So same idea, we're going to have reaction progress over here. So we're going to kind of look at energy as we start out at C and we go to D, and we're going to measure the energy. But this time, our starting material C is going to be lower in energy than our final product D. Well, same idea though, right? We can say, well, we can measure this gap in energy. But this time, delta G is going to be flipped. Delta G is going to be positive. And another way of describing this is we could say the reaction is non-spontaneous, meaning it simply won't occur under these conditions. And that's because the products are less stable. And this would be an endergonic reaction. All right, so it's pretty interesting. Chemists are always obsessed with measuring the energy of these various systems, right? It teaches us a lot about what's going on in these processes. All right, so let's take a look at some of the math parts here. And again, this goes way above and beyond the book. So this is more just to clarify any questions you have from the book, but if you find the book's explanation to work, then go with it. So variables that impact reaction spontaneity. Whoops. All right, so we know that if delta G is negative, I'll just put it like this, then the reaction is spontaneous. However, if delta G is positive, we know the opposite is true. So the opposite is true. The reaction is non-spontaneous. All right, so how do we determine these values of delta G practically? Well, there's an actual math equation we can use. And here's the math equation. It says that delta G, that change in Gibbs free energy, is going to be equal to delta H, which is really looking at heat energy because that's one type of potential energy we can have. But then that's not the whole picture. We also have another side of this equation that looks at another form of potential energy that we can store up in the form of what is called entropy. So let's quickly identify each of these terms. So this is the enthalpy change. And what this is it is heat in or out. So it's really asking, is the reaction endothermic, meaning are we putting heat in, or is it exothermic? Are we getting heat out of the reaction? That's a kind of simple way of viewing enthalpy. There's a little bit more to it, but that's a simple way of viewing it. All right, T in this case is going to be temperature. But this temperature, just like with gas laws, is going to be measured in Kelvin, meaning it can never be a negative value, right? Kelvin is always from 0 and up. You don't have negative Kelvin. All right, and then last is this delta S, and this is the entropy change. And so what is an entropy change? It's a measure in the change of disorder. All right, so you can imagine if you pack things tightly, they aren't really happy that way. That's stored potential energy. They want to spread out and be far away. So that's why I don't like the book explanation, is we need to really tease apart the energy contained within heat and then the energy contained within systems that are highly ordered, right? Highly ordered things naturally want to become disordered. All right, so let's take a look at this in a bit more detail. And like I said, delta H is a measure of heat in or out. And it's actually not too bad to remember. So first things first, delta H is negative if the reaction is exothermic. And what does that mean? Well, it means it releases heat, if you remember. All right, and then the opposite is true, that delta H, the change in enthalpy, is positive if the reaction is endothermic, meaning it absorbs heat, or it requires heat for that reaction. Okay, so those are really important to know. I'll go over here and write the book definition. And it's kind of something that frustrates me, but they just simply refer to this as a decrease in energy. Let me go ahead and slide this over. All right, versus over here, if delta H is positive, this is the same thing as the book saying an increase in energy, meaning heat was put in. But like I said, it's my pet peeve because they're not really being clear about the energy here, right? So that leads us to our next point. Let's look at entropy. That's the delta S symbol. So change in entropy measures disorder. Okay, so these ones are going to be looking at whether or not they're positive or negative as well. So delta S is positive if reaction product is more disorder. All right, and then the opposite is true, where delta S is negative if reaction product, or actually I'll just say product here, because like I said, it doesn't need to always be a reaction, it could be something as simple as a phase change. Is less disordered. All right, so let's take a look at this in a little bit more detail. So let's look at things that can make things more disordered. And there's a variety of different things that could actually impact this. So for example, first one is we could have more moles of product than the starting materials we put in. And I'll just call product PDT. So that's a simple one, right? Another thing we could consider is a phase change where we're going to a more disordered state. So what do I mean by that? Well, think about going from a solid to a liquid, right? Solids are neatly packed, liquids are not. They move around a lot more, they're less disordered. Or we could imagine going from a liquid to a gas. Something like that would also lead to more disorder of those particles, right? All right, and then the last one is if your product is more floppy. And I know this isn't the correct scientific term, but what does that mean? Well, imagine that we start out with a circle and then we cut it open into a straight line, right? So imagine we've got these little chemical scissors and we just chop this open. Well, in this case, it's less tied up and it's more floppy, meaning this line over here could kind of wiggle around like a worm where the circle is kind of constrained. This is something that we're not really going to talk about, but I felt like I should present it. All right, so now let's take a look at some problem solving with this. And I know this isn't in your book, so bear with me. We're just going to take this simple equation. We're going to say delta G equals delta H plus negative T delta S, right? And in fact, we also said that if delta G is negative, that the process is spontaneous. And then we said if delta G is positive, then the process is non-spontaneous. All right, and in fact, let's go ahead and flip these around, and you'll see why here in a second. But I'm just going to go ahead and move this all up a little bit. And we're going to make a little chart. So we know that the main variables that we need to really focus in on are the delta H and delta S symbols. So I'm going to make kind of a Punnett square, if you remember that from biology. And we'll do kind of crossbars here. So up here, I've got delta H is going to be positive versus delta H down here will be negative. Then up here, I'll do delta S is positive, and then I'll do delta S is negative. All right, so let's focus in on one of these right here, right? So actually, let's do this one down here. All right, so in this one, you can see that we're dealing with delta H that's negative and delta S that's positive. Well, let's think about that. So if delta H is a negative value, and we go ahead and we add it to this component, right? Well, this component, we said that delta S would be positive, but we've got negative T. So a positive times a negative would be a negative. So that means that a negative plus a negative will always give you a mathematical result that's negative, which again tells us that this process will always be spontaneous if these two things are true. So let's go ahead and write this all out. Okay, so this would be a spontaneous process. And this is true always. Doesn't matter what temperature we plug in, a negative plus a negative, always going to be a negative, right? Well, now let's do the opposite, right? Let's go over here. So on this side, we've got delta S that's negative and delta H that's positive. So same idea. and say, well, this time delta H is positive, and then over here, we need to look at this a little bit more carefully. So if delta S down here is a negative value, and we're multiplying it by negative T, a negative times a negative is going to be a positive. So now we've got a positive plus a positive. That's always going to result in a delta G value that's positive. So this tells us that if these conditions are true, that this is going to be a non-spontaneous process. And this is true always, right? It doesn't matter what the temperature is. A positive plus a positive is always going to give you a positive result, right? All right, now let's get into the tricky ones. Let's go into this lower quadrant right here. So in this case, what if delta H and delta S are negative? So what does that mean? Well, if delta H is negative, it's exothermic. If delta S is negative, it means things are getting more ordered. So let's go ahead and look at this. So up here, exothermic means that this would be a negative value. But now we've got a negative times a negative again, which tells me that the net result of this whole thing in parentheses will always be positive. So now the question is, well, a negative plus a positive, what will the sign be? And I would say, well, it depends, right? Is this a really big negative value, or is it a really small negative value? Or conversely, is this a really big positive value, or is it a really small negative or small positive value? So this leads to a situation. Down here, we can say that it's spontaneous, but only at a specific temperature. And let's determine what temperature we'd need. Well, if we want it to be a spontaneous process, we need the delta G sign to be negative, right? Which means that we want this half of the equation to really win out on that negative tug-of-war, right? So this would occur, but in order for this to occur, we really need to minimize this T, meaning it needs to be at a low temperature. So this is a spontaneous process, but only at low temp. So let's take an example of this, right? So in this example, let's imagine that we've got water freezing. So I'm going from H2O liquid to solid water, right? Let's think about if we put heat in or if we get heat out. Well, we definitely don't put heat in when we're trying to freeze water, which means we're going to get heat out. In fact, that's what your fridge does, or freezer, is it pulls away this heat that's formed. Okay, so let's think about this. If we think about it, we would say that, well, in this reaction, delta H is going to be negative, right? Because it's an exothermic reaction. So delta H would be negative because it's exothermic. However, let's think about entropy. Does it get more ordered or more disordered? Well, in this case, I would say it gets more ordered, or another way of describing that is we're losing our disorder, which means that this would be negative, meaning less disorder. All right, so now if we think about this in freezing water, does it occur at all temperatures? No. This process is only spontaneous at a low enough temperature. That's what's going on here. All right, and then last but not least, we can do the same thing with our remaining spot. We can say, well, what if they're both positive? All right, well, if that's true, then this would be positive, and then a positive times a negative would be a negative. Same idea, but it's going to be flip-flop this time. So this would be spontaneous, but only at high temp. So you could think about boiling water. That would be another analogy we could use here. But it's all based on this math. And instead, the book just says, here's a few situations where these are true. Just try to memorize them. I'm definitely not built that way. I kind of want to see this broken down. But if the book makes sense to you, try to stick with that. All right, I apologize. I know this video is long. But let's just cover part 8.2 or section 8.2 because it's really quick. All right. And this is just going to be a quick note as it relates to spontaneous reactions. So this note is that spontaneous reactions are not always fast. All right. It's kind of weird to think about. So why aren't they always fast? Well, let's think about it this way. So let's think about the Grand Canyon. Was formed spontaneously. All right. So if you imagine the Colorado River, millions of years ago was up much, much higher. And then over time, it's kind of working its way down, which is what's digging the canyon out. All right. But it took millions of years. So yeah, it's getting lower in energy. It's releasing energy in that process. But it takes a long, long time. All right. Another example is I am spontaneously decomposing. All right. So you might be wondering, well, what in the heck does that mean? Well, imagine this sort of process. This is me as a stick person. Eventually, a while from now, I'll be in the ground and mostly converted to water and carbon dioxide, plus, a few other things. All right. This is occurring spontaneously, but it's my hope that it's not going to be a fast process. I'm hoping to eke out, a few more decades here before I turn into water and CO2. All right. So how do we measure rate? All right. So it's pretty easy. Reaction rates can be measured by measuring the change in concentration of a product over a change in time. Oftentimes you just see this written as delta C over delta T. And so what does delta C equal? It's going to be equal to your final concentration minus your initial concentration. All right, and then if you know your time as well, you can basically determine the rate of an overall reaction. All right, again, like I said, the book explains things differently, but I felt like I had to explain it more thoroughly because I'm a chemist, and I read it and it just confused me. So hopefully this helps you, but if you have questions, feel free to email me.